Okay. So I'm going to start with the next topic, that is dynamic stereochemistry. Now, what is this dynamic stereochemistry? Dynamic stereochemistry is nothing but we talk about the uh, different aspect, structural aspect of the reactant with respect to the rate of reaction. We just determine the stereochemistry of the starting material and the product. We just have a relationship between them. We talk about the kinetics also, what is the rate of reaction between the two isomers of any starting material. जैसे for example, if I have a cyclohexanol, when I say cyclohexanol, cyclohexane होगा and उस cyclohexane पे will have the OH. Now this OH can have axial position or this OH can have equatorial position. तो मेरे पास दोनों structures available है. So what we do, we try to perform different reactions on the axial alcohol and the equatorial alcohols. Okay. And then we see which particular alcohol will be faster in reaction. जैसे stereochemistry इनका अलग अलग है. Cyclohexanol, one is the axial, this one is axial, and this one is equatorial. Of course, the stereochemistry is different. The kind of approach we have is different. If you see this particular OH, यहाँ पे proton है. They will have this 1,3 diaxial interaction, but this 1,3 diaxial interaction will be stable here because that is kind of hydrogen bonding here. Okay, so generally we say the substituents are more stable in the equatorial position, but in case of OH it will be more stable at the axial location. Okay, so while looking at the stereochemistry of that starting material and then relate it to the product, the kind of product which we are forming, which is very important, then try to relate which one is going to be faster in reaction compared to the other. So that relationship we need to find out. But everyone knows that if I'm talking about this particular starting material, ये जो starting material मैं देख रही हूँ, तो ये OH फिलहाल कहाँ पे है? That is at the axial position, and this OH if you see equatorial position. Is it possible to fix it at this location? Be this particular molecule originally, is it rigid? So we need to fix it, right? So how to fix it? Third butyl group at this kind of position. So what is the reason that we are saying ki we need to fix it or we need to make it rigid? So I'm making it rigid by attaching this temporary functional group at this location. So now we call this as which system? We call this as an encomeric system. Okay, this word I have told you last time also. So I made it an encomeric. Why I made it an encomeric? Because I told you we are dealing with the stereochemical course of the reaction. So during that stereochemical course, we talk about what are the bonds which are formed, what are the bonds which are broken, then which alcohol will be faster in reaction. Suppose if I don't attach this bulkier group, what will happen? If I allow this to undergo oxidation, see your reactant is going to flip from one form to other form. तो ये जो axial है कुछ form में equatorial बनेगा, ठीक है? Rate of reaction, the ring flipping is faster. See what I'm saying? कि इन दोनों का flipping एक process है, right? And then this is converted to my product. So ये इसका एक rate of reaction है. This is my rate of reaction, and this is a rate of flipping. But if I see, if I don't attach this tertiary butyl group, the rate of flipping will be more compared to the rate of reaction. So as a result of which, can I confirmly say that whatever rate of reaction I'm getting is only because of the axial alcohol? Because the rate of flipping is very high. So it may happen that some axial may get converted into equatorial, and that equatorial may give me some reaction in that particular oxidation process. So I don't want any conversion of that axial to equatorial because I want confirmly the rate of axial alcohol. That is nothing but the dynamic stereochemistry. Dynamic stereochemistry, it is going to deal with all your rate processes, any chemical reaction involving bond breaking, bond making process, It is simply we talk about the conformational transformation which are happening during the reaction, relating a stereochemistry of the starting material with the stereochemistry of the product is our aim in the dynamic stereochemistry. But whatever results I'm going to get, I need to be sure about it that I'm getting it from this reactant only. That if I'm starting from the actual alcohol, I should confirmly say at the end of the reaction that I'm getting this entire reaction from actual alcohol, and hence I need to fix this alcohol, that is OH, at the actual location by attaching this tertiary butyl group at the equatorial location. Okay, so dynamic stereochemistry, of course we deal with all these stereochemical processes, but of course it is very important to select the starting material. As I said, in dynamic stereochemistry we are going to relate the stereochemistry of the starting material with the product. We are going to talk about the uh, rate of reaction difference between the two different reactants, conformational isomers. So we should be very sure about our starting material. If I've started with axial, I should end up with the axial only. That means throughout that conformation should not change, and therefore the topic called as the selection of substrate is very important. Okay, so I'm dealing with the dynamic stereochemistry, but in dynamic stereochemistry I've just introduced you what is dynamic stereochemistry. But if at all, if you want to study the dynamic stereochemistry, the most important aspect is selection of substrate. So if I'm doing any reaction, what kind of substrates we are going to select, that we're going to talk about it. Okay. So as I said, there are some molecules which are conformationally rigid. Suppose if I'm doing any study on decalin, okay, you have studied the conformations of decalin, cis and trans. Which one is the most stable one? Is the most stable one. So suppose if I have to study any reaction related to the decalin, I will prefer to take the trans decalin as my substrate rather than cis, because I know that if I take the cis have a problem of ring flipping. So during ring flipping, what will happen if I will start with the axial alcohol that may not remain as axial, it may get converted into equatorial because of ring flipping process. So if I'm doing any conformational analysis on decalin, I should select the trans decalin as a substrate. Okay, because the trans decalin, their all bonds gets locked into the different position because of their rigid structure. हमने ये already पढ़ा है that A and B ring, they cannot undergo any kind of ring flipping in trans decalin. What is the reason that they never undergo this kind of ring flipping? During the ring flipping, one of the ring gets opened up, and therefore it is not possible for them to undergo the ring flipping process. Therefore we call them as conformationally rigid. Originally these molecules are stable in nature. So in these molecules, suppose if I have to do the study, let's say I have given you example on the screen, you can see here we have this equatorial alcohol and we have this axial alcohol here. Okay, so now what we have done the acetylation. Everyone knows the acetylation reaction, that we can do it with the help of acetyl chloride, or we can use acetic anhydride. Different conditions you can use here. So when this study was done, the rate of reaction was calculated. You can see the rate constant here, it is 1, and here the rate constant is 0.13. We can confirmly say whatever the rate constant 1 we got it, it is all of because of the equatorial alcohol. And I can confirmly say whatever the rate I'm getting for the axial is only because of the axial. So here, if you look at the comparison, we can see the equatorial alcohols reacts faster compared to those axial alcohols. Okay, of course the reasons are different. We are going to talk about these reasons later on, but right now what we are talking is, if I have to compare the rate of reactions, the selection of substrate is very important. Now, instead of this trans decalin, if I would have taken the cis decalin over here, okay, it is going to give me the proper result. I cannot say, because they are facing the problem of ring flipping. So, when I'm going to start from the equatorial alcohol, material, then what kind of substrate you will take for the study of dynamic stereochemistry. Okay, so if you are dealing with the conformationally rigid substrates like this, if you are dealing with the systems like decalin or hydrindane, or if you're doing any study on steroids, let's say, then prefer to go for those particular structure which have the rigid conformation. Okay, so just say if I have to do the study on hydrindane also, everyone knows that even you have studied the trans hydrindane is a most rigid structure, so we can go for the trans hydrindane study. If I have to go for the steroids, you have studied two series. One is 5 alpha and one is 5 beta, right? So which one you will take for the dynamic stereochemistry? 5 alpha series or 5 beta series? What is 5 alpha series?
5 alpha, it is trans.
It is trans. Okay, so I will prefer to go for the 5 alpha series where the two, that is A. If you talk about the steroids, we have total 4 rings, right? The A and B ring, sorry, this is A and B ring. Then we have this C ring, and then we have this 5 membered D ring. So A, B, C, D. C and D there is no changes, but especially A and B may changes hoga. A and B, if it is transfused, then we call it as a 5 alpha series, and if it is cis fused, we call it as a 5 beta series. So if I have to go for dynamic stereochemistry on steroids, better to take 5 alpha series as a substrate. Okay, so those results will be the confirmed results. Those results will give us the complete idea about the property of that substance. Okay, but suppose if I don't have the rigid substrate, जैसे we have already discussed about this cyclohexane, if I have this axial alcohol and if I have this equatorial alcohol, okay, I cannot go for the dynamic stereochemistry with these substrates, because we know that these substrate by nature they are not conformationally rigid, but we can make them rigid. Okay, that reason everyone knows, the solution everyone knows. What is the solution to make them rigid? Of bulkier group. So when you put the bulkier group, what happens? These groups gets locked at their position. Okay, now for example, let's say this one. Now we can see the additional this bulkier group is at equatorial location and OH is at axial location. If suppose if they try to flip, what will happen? If the flipping at all happens, what will happen to this tertiary butyl group, which is at equatorial position, that will go to
Axial position.
axial position. But at axial position, it is not going to be stable, because tertiary butyl group, if at all comes at the axial location, for example like this, see what will happen, this tertiary butyl group go at the axial location, और ये जो तुम्हारा OH है वो equatorial location पे आ जाएगा, right? In this particular position, what will happen to this tertiary butyl group? It is going to experience this 1,3 diaxial interaction, and this repulsion is going to make this structure unstable, so it is not possible to flip the ring to this structure. So what will happen, in short, indirectly, all these groups will get locked in this location, because ring flipping is not possible. So we are going to make some temporary changes in the molecule so as to lock their locations, equatorial and axial locations, and hence we call this system as anencomeric system. So anencomeric system is the system which is made rigid by attaching some bulkier group, and this particular bulkier group will not allow this particular ring to undergo any kind of ring flipping process. तो यहाँ पे भी अगर तुमने देखा है, यहाँ पे OH X की जगह, X is nothing but OH only. So they have done the acetylation. First, you can see this is for the equatorial alcohol. The rate is 10.65 into 10 is to minus 5. and here it is 2.89 into 10 is to minus 5. So we can see again the equatorial alcohols are reacting faster compared to the actual alcohols. Okay, अब ये reason एक टेंटेटिव पता चल रहा है क्यों इक्वेटोरियल फास्टर है रिएक्शन में. वो x की जगह पे क्या है?
alcohol,
अल्कोहल OH है,
OH,
राइट. OH एक्चुअल पे स्टेबल कैसे हो गया? रेट ऑफ रिएक्शन क्यों उसका स्लो है?
hydrogen,
हाइड्रोजन बॉन्डिंग. यहाँ पे ये जो है ना, these hydrogens, they're going to cause hydrogen bonding. That's why I told you actual alcohols are more stable, and therefore they will not prefer to give you any reaction faster. But equatorial alcohols will react faster. One more reason is there. Which group you're going to add here? Acetyl group. What is acetyl group? CH3 C double bond O, right? ये ग्रुप वहां पे ऐड करने वाले हो तो. So if you look at this group, incoming group, it is going to come at the actual location, and this incoming group अगर यहाँ पे आया तो वो इक्वेटोरियल पे जाएगा, तो वो कहाँ पे ज्यादा स्टेबल होगा? इक्वेटोरियल पे ज्यादा स्टेबल होगा. इट इज बल्कियर, सो इट विल बी मोर, इट विल प्रिफर टू स्टे एट इक्वेटोरियल लोकेशन rather than actual location. Okay, this reason I have just told you here, this reason is not important. We are just finding out, if suppose if you are dealing with the cyclohexanol, if I'm taking cyclohexane derivative for the dynamic stereochemistry, how can we make that system more rigid? Okay, now when we have a system like they are conformationally mobile, but we cannot even make them rigid by attaching some substituents. For example, look at this system. ये वाला स्ट्रक्चर देखो. अगर तुम देखोगे इस स्ट्रक्चर में all the bonds which are, you can see, they are all open chain. Okay, so if you have this kind of open chain, it is very difficult to restrict. For example, you must have studied this, एक सिंपल इथेन सिस्टम अगर तुम देखोगे तो ये कार्बन कार्बन सिंगल बॉन्ड है, that is going to flip a lot, and जब भी flipping होगा you will get two type of Newman projection, right? One will have the staggered conformation like this, and one will have the, sorry, one is with having the eclipsed and this is staggered, दूसरा staggered होगा. Okay, there are of course new, there are a lot of conformations possible, but ये जो है वो हम extremities discuss कर रहे हैं. ये eclipsed वाला है और ये staggered वाला है. अब इन दोनों में flipping इतना होता रहता है, and even if you see the energy difference between this eclipse and staggered form, it is just 3 kilocalories per mole. These 3 kilocalories per mole, if you see, any reaction condition can give this energy. So it is not possible to restrict the ethane in that staggered conformation. Though we are saying it is more stable, staggered conformation is more stable, but ethane is not going to have more population of 100% population of staggered. It may have some percentage of the eclipse as well. Because as I said, the difference in energy between the eclipse and the staggered is just 3 kilocalories per mole, and that can be provided very easily from any reaction condition. So now if I have to make this particular structure, ethane को मुझे rigid करना है, is it possible for me to restrict the conformation in the staggered? That will make a difference. Staggered form में कभी भी conformation को rigid नहीं कर सकते हम, because it's an open chain. Open chain conformations are very mobile, conformationally mobile diastereomers. We cannot make them rigid. ओके, तो जैसे हमारे पास डेकेलिन का प्रॉब्लम था, हमारे पास इजी सोल्यूशन था, बिकॉज डेकेलिन सिस्टम एक कॉन्फर्मेशन ट्रांस इज मोर रिजिड, तो वी कैन टेक दैट सबस्ट्रेट. साइक्लोहेक्सेन पे आए तो साइक्लोहेक्सेन दो इट वाज अ कन्फॉर्मेशनली मोबाइल, बट वी अटैच टर्शरी ब्यूटाइल ग्रुप टू मेक इट रिजिड. But if you look at this kind of open chain structure, is it possible to make them rigid? It is not at all possible to make them rigid. So how to deal with this? Now if I'm doing the dynamic stereochemistry on these kind of substrate, how to restrict them? Because they are going to flip from one form to other form very easily, so they are going to be mobile throughout. तो ऐसे केस में हम उनके स्टीरियोकेमिस्ट्री के बारे में कैसे जज करते हैं, या उनके डायनामिक स्टीरियोकेमिस्ट्री को रिजल्ट को इंटरप्रिटेट कैसे करते हैं, दैट वी आर गोइंग टू टॉक. ओके, वी आर गोइंग टू we are talking about the selection of substrate. Like for any substrate, it is not necessary we are going to talk about only ring system. Open chain system भी आ सकते हैं dynamic stereochemistry में. So any type of substrate you have, but how you're going to interpret the results, is very important. How you're going to select the substrate for your study, that is very important. So now in this case, if you look at this particular structure which we have started, again I have taken two different isomers. I have taken its threoisomers, I have taken its erythroisomers. Okay, now let us talk about the first one, 301. Okay, whatever reaction here we are dealing with, how we have predicted the major product, or how we have related the stereochemistry of the starting material with the product, that we're going to talk. Okay, now in this case, first of all we'll draw the Newman projection. तो यहाँ पे जब न्यूमैन प्रोजेक्शन देखेंगे, we will see the Newman projection across this 2 and 3 bond. Okay, so now there are three different Newman projections possible. So first of all, understand that I'm taking this second carbon in front and the third will be back. So I have this second carbon. If you look at the second carbon, there are three bonds to that second carbon. Okay, three substituents. एक है pH, एक है COOH और एक है H. So I'm drawing it as it is. One is COOH, one is pH and one is H. मैंने देखो as it is इसको draw किया. Okay, now on the back side I have this third carbon, and this third carbon, it is attached to the three different substituents. Again I'm drawing them. The first one is H, second is pH, and the third one is CH2pH. This is a one conformation which is possible. Now I'm drawing another conformation, but I'm going for only staggered. I'm not going to draw any eclipsed. Okay, because we know that between eclipse and staggered, staggered is more stable. Okay, so why to go for eclipse unnecessary? We have to find which is the more stable conformation. So what I'm going to do here, I'm going to fix this front carbon as it is. So I'm drawing as it is. COOH, pH, and this H. Again, the back carbon, I'm rotating it. I'm taking pH here. So H will go on this side and CH2OH will be, sorry, CH2pH will be down. This is another conformation which is possible. And then the third conformation. Again, the front carbon I'm keeping as it is. Again, I'm rotating it. So pH is now on the right side. H is down, and this is CH2pH. So this is first staggered conformation, this is second staggered conformation, and this is third. So there are three staggered conformation possible. तो वैसे ही three eclipse भी possible है. अभी फिलहाल हम eclipse के बारे में बात नहीं करेंगे because we are going to talk about the most stable conformation. Okay, that's why I've taken three staggered. Now you discuss with me, what about the stability of these three? Which one is more stable? First one, because now here we can see the two pH groups are close, still they're gauche. These are also gauche, but these two gauche, if you see, they are anti to each other. Ye first gauche hai, let's call it as A. This is second gauche, right? But look at the first and the second gauche, they are anti to each other. अब यहाँ पे देखो, these two are gauche to each other, these are also gauche, these are also gauche. तो यहाँ पे कितना रिपल्शन है? यहाँ पे थ्री वे रिपल्शन है. Similarly, if you'll see this, right, they're also gauche. So out of the three, which is the most stable structure? The first one is the most stable structure. So what generally the rule says, suppose if you have this kind of conformationally mobile diastereomers, and we cannot even make them rigid by attaching some temporary substituents. So in this case, we consider the most stable conformation of it, and we say, or you can say we say that the whatever product we are getting is because of that most stable conformation. तो अब हमने क्या किया, इन तीनों में से हमने सिलेक्ट किया फर्स्ट वन, और मैंने देखो यहाँ पे फर्स्ट लिखा हुआ है. Okay, so I'm going to consider only the most stable conformation of it, because now I will say this particular compound will exist in different conformation form, but usme se the one which is majorly populated, which one will be majorly populated, the one which is more stable. So suppose अगर ये 60% है तो ये 20% होगा और ये 20% होगा, राइट. ये और ये दोनों में तीन तीन इंटरेक्शन है, तो ऑफकोर्स अगर इसका पॉपुलेशन 20% है तो इसका भी 20% होगा, एंड दिस विल बी मोर पॉपुलेटेड. So I have considered the more populated substrate here. Okay, now here I'm going to allow this to react with HF. Now what is going to happen, understand. Okay, here I have this COOH. Here I have this COOH, right? Now this particular COOH is going to get interacted with this CH2. अब exactly यहाँ पे reaction कैसे होगा, that you understand. First of all, we have this particular what you say this particular pH group. अब ये pH group को मैं पूरा डिटेल में ड्रॉ करती हूँ यहाँ पे. ओके, यहाँ पे एक H है देखो, राइट, एंड दिस पर्टिकुलर कार्बोनिल ग्रुप, it has this OH here. So what will happen? They will undergo the loss of water molecule. This water molecule will be lost, condensation will happen. So now what I'll get, this C double bond O, where it will be bonded, it will be bonded to this benzene ring with the loss of the water molecule. Can you see this CO carbonyl group is bonded to benzene ring, because from here what has lost, water has lost, right. अब देखो, this CH2, ये CH2 इस bond को कैसा है, ortho पे है, देखो. So this CH2 is at ortho. This is my CH2 group. CH2 कहाँ पे bonded है, next देखो, backside carbon पे. Backside carbon जो है, it is attached to what? It is attached to pH. So this CH2 is bonded to this carbon which is attached to pH. Backside carbon is attached to what? Front side carbon, which is also having pH. Backside carbon is attached to the front side carbon, which is also attached to pH, and the backside, sorry, front side carbon is also attached to carbonyl. तो यहाँ पे ये ring join हो गया. Clear, समझ में आया? This is called as tetralone. The product which we are getting here is a tetralone system, and we are saying that tetralone is formed because of the most populated conformer of this structure. तो हमने वही सबस्ट्रेट कंसीडर किया है जो मोस्ट पॉपुलेटेड है, एंड देन वी हैव रिलेटेड द स्ट्रक्चर, दैट इनिशियल रिएक्टेंट विद द प्रोडक्ट. So we are saying this product is formed because of this conformation only. Okay, so when your substrate is having a lot of conformation and they're very mobile, then we consider only the substrate having the highest population. Okay, now similarly if you look at the next one, erythro one. अब एरिथ्रो पे भी दो कार्बन है, देखो, दिस इज सेकेंड कार्बन, सॉरी, वी आर गोइंग टू सी द रीमेन प्रोजेक्शन अक्रॉस द सेकेंड एंड थर्ड. अगेन आई एम गोइंग टू कीप द फ्रंट कार्बन एज इट इज. सो फ्रंट कार्बन पे क्या क्या है, COOH है, दिस वन COOH, PH and H. So PH and H. A backside carbon, again there are three different conformations possible. तो backside carbon पे यहाँ पे मैं लिख रही हूँ PH, this is H and this is CH2PH. एक conformation ये हुआ, ठीक है. Another conformation, front carbon मैंने as it is रखा, backside को rotate करो. So PH will come here, CH2PH will be down and H will be here. This is second one. And one more conformation, COOH, front carbon as it is, PH and H. Okay, and then I will have pH down. Sorry, it is not possible to write. This is CH2 pH here, and this is H here. अब बताओ कौन सा stable है?
Second one.
Second one is more stable. So we are going to consider only second one, because here other three will have, sorry, three interactions. So of course अगर ये 60% हुआ populated, तो ये 20% और ये 20%. See, मैं example दे रही हूँ ना, अगर ये 80% भी हो सकता है, ये 80% हुआ तो ये 10%, ये 10%. I'm just giving example of that. तो हम सिर्फ consider कर रहे हैं अभी second वाला. So I've written the second one. Okay. अब दोनों में difference क्या है देखो, इसके कॉन्फर्मेशन में और इसके कॉन्फर्मेशन में डिफरेंस क्या है? COH को जो गॉश था वो कौन सा ग्रुप था? CH2PH ग्रुप था. अब गॉश कौन है? पीएच ग्रुप है, ओनली पीएच ग्रुप. सो अब यहाँ पे प्रोडक्ट देखो कैसे चेंज हुआ. द सेम थिंग इज गोइंग टू हैपन. हियर आई हैव H and this carbonyl group will lose OH. So there will be loss of water molecule. Same thing is going to happen. C double bond O attached to benzene ring. Benzene ring is attached to the backside carbon, which is having CH2PH group. It is attached to the front side carbon, which is having the pH group, and it is attached to carbonyl group. सिर्फ वो CH2PH नहीं था तो ये देखो, ये रिंग में देखो कितना डिफरेंस आया. ये 6 मेंबर रिंग बना और यहाँ पे ये 5 मेंबर रिंग बना. सो टेट्रालोन का बना इंडेनोन. Okay, so if you see, the trio is giving me the tetralone formation and erythro is giving me indenone conformation. ये हो गया dynamic stereochemistry. We are relating the stereochemistry of the starting material with the product. But how we have decided it? By selecting a substrate which is having highest population. Okay, only the substrate having the highest population is to be considered. Again, I'm repeating, if you can have a conformationally rigid system, then take that for the study. If you can make it rigid, then it is called as an anencomeric system. We can use that for study. If you have this kind of conformationally mobile systems, then consider the most stable isomer or most stable conformation, or simply we say the most populated conformation is considered for the study. और एक एग्जाम्पल मैंने दिया देखो, we can depend on, we can say the most populated one we can take for the study, or there is one more rule. If you have this kind of conformationally mobile systems, there are two rules. एक तो उसका highest population consider करो, और second thing, look at the stereochemical requirement of the reaction. For example, if you look at this example here, I've taken two starting materials. One is this cis type of structure and one is this trans type of structure. Okay? So we have taken this isomers. So you can say this is also, this is the meso one and this is plus minus, ye plus minus hai tumhara, or ye meso isomers hai. So you can say that also. Now when you have this kind of substrate, I'm going to do the debromination over here. Dibromo group को निकालना है और alkene form करना है. Now, what is the stereochemical requirement of this group? The stereochemical requirement says these two living group that do bromines, when they're going to leave from opposite side. तो ये तभी possible होगा, ऐसा कॉन्फॉर्मेशन होना चाहिए जहां पे वो अपोजिट साइड पे हो. जैसे फॉर एग्जांपल, इफ आई एम गोइंग टू ड्रॉ the Newman projections or the Sohaus projections for this, I can have different conformations possible. So what I'm doing, I'm keeping this as it is: bromine, H and CH3, CH3, H and bromine. This is one structure possible. Second structure, I'm keeping the front carbon as it is, H, CH3. बैक को मैं चेंज कर रही हूँ, यहाँ पे Br आएगा, यहाँ पे CH3 आएगा और यहाँ पे H आएगा. This is second one. Or third possibility, this one. CH3 will be down, H here and bromine here. Okay, so these are the three one. नाउ अकॉर्डिंग टू द प्रीवियस रूल हम क्या कर सकते थे, हम कर सकते थे मोस्ट पॉपुलेटेड कौन है उसको हम कंसीडर कर सकते थे, बट the reaction says when the two bromines are going to leave, they're going to leave from opposite side. Anti elimination is the rule, right? तो anti elimination होगा तो 1 2 3 ये तीनों में से मुझे वन ही कंसीडर करना पड़ेगा. Why? Because that is only structure where I have these two bromine groups which are anti to each other. Though this first isomer is not more populated, you can say it is less populated amongst the three, but only that will undergo the reaction because the stereochemical requirement of the reaction says the two group has to be anti, so we're going to consider that structure only. So I've considered here, see, you can see here, this is the first conformation I have selected here. Now these two bromines group are going to leave and the double bond will form here, so that you can see the two CH3 groups are going to be anti to each other, so I'm going to end up with trans product. Okay, but similar case जब हम plus minus isomer से start करते हैं, again here there are three different conformations possible, but we have selected the one which is having the bromine anti to each other. अब यहाँ पे अगर डबल बॉन्ड फॉर्म होता है then I will have two CH3 groups on same side, so I'm going to end up with cis. So the dynamic stereochemistry says when I start with a mesoisomer I get the trans alkene as a product, and when I start with plus minus isomer I end up with a cis alkene as a product. And how we have decided this? By selecting the conformer which is satisfying the stereochemical requirement of the reaction. Clear to everyone? यहाँ पे मैंने दो एग्जाम्पल देखो कवर किए. इस केस में हमने वो कॉन्फॉर्मर कंसीडर किया जिसका पॉपुलेशन सबसे ज्यादा है, और इस केस में हमने वो कॉन्फॉर्मर कंसीडर किया विच इज सेटिस्फाइंग द स्टीरियोकेमिकल रिक्वायरमेंट ऑफ द रिएक्शन. So this is basically it is applicable for the acyclic system. Okay, for cyclic system we have a different rule. We can make those rings rigid by attaching something. For acyclic system where the conformations are very mobile, in that case we can decide the product stereochemistry on the basis of two rules. Either we can consider the conformer which is highly populated, because if that is highly populated then its reactivity can be considered, and second case we can say we can consider that conformer which is having the stereo or which is satisfying the stereochemical requirement of the reaction.